All right, so I'm Richard Boyd. I'm here today to talk to you about a revolution that's happening today in technology and about a little company that we started up here in North Carolina, completely North Carolina funded, as all of our companies that we've created here have been in North Carolina. This one's in lovely little Carborough, and we're focused on what we think is one of the most important technologies to be leveraged today in the information age, and that is machine learning. A little bit about how we got there. My co-founder, David Smith, and I, and actually all the co-founders of this company, have worked together for quite some time. We've worked in the computer gaming industry, in aerospace, in the film industry, and with artificial intelligence. And it may seem unnatural to come by that path to get to where we are today, but it actually makes a lot of sense when you understand that artificial intelligence has always been a part of gaming. If you want to make really convincing environments with convincing characters to interact with, then you have to have a firm grasp of how to create these synthetic people. But the thesis statement for us today is that really the central problem of this century is how to achieve the right balance between humans and automation to optimize the outcome. Anybody who gets that right is going to prosper, is going to prevail over those who don't get that right. And pretty soon, if you're not leveraging machine intelligence, especially machine learning, you're going to be considered handicapped. I think you could get away with it last year, but if you're an enterprise, if you're a government, and soon I think if you're an individual, if you don't become fluent with these technologies, understand how to get that man-machine balance right, you won't be competitive here very soon. You won't be able to get away with this next year. So let's talk about what that means. It was interesting to me to look at the political commentary over the last year and see that hardly anybody was really talking about what's happening in terms of automation disrupting our very way of life. It's disrupting our social structures, our political structures, and again, we need to pay attention closely to it, but also we don't need to be victims of this. After all, this is technology we created, right? So we can take advantage of it and make it work for us. And that's what our little company is all about. We're helping Fortune 100 companies, Fortune 50 companies even, and even sort of mid-sized and small-sized professional firms learn how to employ it today, within 30 days, and begin to get it right and customize it so that you do have that competitive advantage. I wrote an article back, you see on the screen there, back in a couple of years ago, talking about that man-machine balance. It was in TechCrunch, saying that we're actually driving the next stage of machine learning. Again, some of us are, some of us aren't. That's something, again, that's important to get right. So what you're looking at now is it begins, I think, in 2007. And as this builds over time, you'll see it grow to about 2017. Actually 2011, I think. This is what the World Economic Forum in Davos was talking about the last 2 years in a row. It was a major theme. All the big leaders of the world flew off to Davos and got together, and they were talking about automation and disruption. So again, it's somewhat remarkable that we weren't talking about this in the political environment, and that not enough companies are coming up with machine learning strategies to make sure that they understand if there's a new capability they're trying to implement. Instead of just going to HR like we did 20 years ago, we need to look at, do you go to HR for that capability? Do you look at R&D internally, or do you look at procurement? How do I go get some automation to fill some or part of that need? And we think, again, I keep talking about balance. The real key is a balance between humans and machines. So as you're looking at this build, these are all actually the trading indices across our financial systems. And the activity you see are actually high frequency trading bots. Now, as soon as I saw this, I fired my financial planner because I realized that he can't help me anymore. us poor, dumb, slow humans with our 200 hertz synapses in our brains, that haven't been upgraded, by the way, since I think the Pleistocene, by my reckoning. We can't keep up anymore. These guys are trading at the speed of light. In fact, it's not enough even to have your own bot or set of bots and algorithms on a really fast machine. It has to be located as close as possible physically to wherever that trading is happening, to the companion trading system you're going to be talking to. So you can't be in Yonkers, New York. You've got to be on Wall Street, hopefully in the building next door to the machines that are actually doing these trades. In fact, in September 15th, 2011, we caught these systems trading with each other in the future. I'm just showing you this to talk about the uneven playing field that we have today and how you need to be implementing these sorts of technologies to level the playing field for yourself or gain an advantage. It's happening a lot faster than any of us predicted, actually. And one thing we know is that government policy tends to trail technology by at least 10 years. In this case, it certainly did. We were talking about this for quite some time, and Michael Lewis just came out with his book a couple of years ago, finally talking about it, and now the SEC is beginning to regulate high-frequency trading. What you're looking at now is a war game that I participated in back a summer ago, where we were looking at the future of our military fighting force. And if you've ever seen these war games that they do, they tend to have you like to have a red team and a blue team. The blue team is our force, the Navy, Air Force, Marines, Coast Guard, Army, everyone. And then there's a red team, which is the adversary. In this case, we were talking about the future forces that would be shaping how our military develops. On the red team here, you'll see myself, Xerox PARC pioneer Alan Kay. This is a USA Today article. Michael Jones from Google, David Smith, my colleague and co-founder here, and some others. And one of the things we came up with that you'll see in that article is we predicted that the fighting force of the future would have 10% or 20% of the same of the number of people, but potentially 20 times the strike capacity. So that's a thing that our systems in our government and in our military are not really ready for. Our HR systems are, a lot of these systems just aren't ready. And the general idea here is that it's happening really fast. And instead of trying to compete with machines, which a lot of people are still trying to do, it's best to figure out how to cooperate with them, how to actually have them serve us instead of us reacting to them. And that's a common theme of everything that we do. The slide you're looking at here is a little video that I did. It's an anime. That's my avatar in this environment, this virtual world we call the Factory of the Future back at Lockheed, where I was for a time. And in this, really what's happening is that there's this age-old struggle between capital and labor has finally it's being settled right now. And guess who's winning? It's not labor, it's capital. So again, if you have a job that you're trying to do, you're going to be paid. If a machine can do it as well, you can expect to be paid as much as it costs to rent the machine and no more. So you need to really think about, again, the central problem is what do humans need to be focused on? Where does our attention need to be and our effort? And what do we need to outsource or put into the automation or machine realm? Now, this is not a new problem. What you're looking at here is the sort of history of what's happened as technology has disrupted the workforce. Now, in the case of agriculture, for example, back in 1800 in the United States, 90% of all of everyone in the U.S. worked in agriculture. 100 years later, 41% of the U.S. worked in agriculture. We were displaced by machines even back then. And today it's about 2%. There's more app developers than there are farmers in the U.S. today. So we had a lot of time in this case, 200 years, to actually adapt to those tremendous forces. And these are technologies we created, and yet we had to figure out a way to adapt to it. The problem today, or the challenge today, is that it's happening at a much more rapid pace. So let's look at how you can actually apply it today. For those of you who are looking at machine learning for the first time, I'll just give you a quick little primer on what it is. Think back to when we first started talking about autonomous vehicles. It was around 2000, in the early 2000s, right? DARPA had their challenge, and we tried to approach it the way that we did with programming back at that time, which is we would not attempt to program anything until we thought we understood it completely. The problem is we don't understand how a lot of things work, right? Even when you're driving a car, a lot of it's done just subconsciously. And so we tried to program everything into these systems with human effort and then put them out there. And of course, the 2004 trials were a dismal failure, where the machines or the autonomous vehicles maybe made it 100, 200 yards across the desert before failing. But then this new technology came along, or this new approach. We've been talking about artificial intelligence for a long time, but it's always been really AI of the last couple of decades is really anything that isn't working yet, right? That's what we called AI. In gaming, we had behavior trees and even hierarchical behavior sorts of trees and rule sets and lookup tables, but it was pretty rigid in its structure. So the big difference with machine learning is that learning piece of it, how the system itself can acquire new information, update its own database, its own memory, its own understanding, and then move forward with that new understanding. That one little difference is absolutely changing everything. So today, even last year, there was a machine learning example in autonomous vehicles where a system just had to watch a brand new clean system with all of its sensors and stuff in a setup for a car. The brain of that system just watched 100 hours of video. And that was enough for it to learn everything it needed to know about operating that vehicle and understanding the sensory input that was coming in from all the sensors around it. And it could go out there and drive flawlessly, 100 hours, right? That's happening really fast. And the central idea here, as you see, what I'm showing you here on the slide is, and this is where I really got religion. This was about 2009. David Smith and I, my co-founder at Tanjo, went to Microsoft Research Labs in San Francisco and sat down with Jaron Lanier, the guy you see in the dreadlocks there, who is the guy who came up with the term virtual reality, and we've known him for quite some time. The other guy is Alex Kipman. He was Inventor of the Year that year from Popular Science, and he was working on a project called Natal, which later became the Microsoft Kinect. And they had a very, it sounds like a simple problem, but it turned out to be technologically complex, which is they only had about 60 megs of space on the Xboxes that had been shipped out to everybody in the world. And they were trying to add this new peripheral that could see and understand everything in its environment. But in order to train the brain, what they had to do is just teach it what a living room was. What does an Asian living room look like? What does a rural versus an urban living room look like? What's a chair? Can I tell the difference between a chair and a couch, or a tree, a potted plant, or a person, or a cat, or a dog? And even distinguish between people. And again, rather than sit down and try to program all the rules into an AI behavior tree of some kind, instead, what they did is used a supercomputer and just gave it lots and lots of examples, and then reinforced the learning of, like, yes, that's a chair, that's a couch, that's a potted plant, that's a cat, that's a dog, and the system itself was able to learn all those patterns, and they got it down to something less than 60 megs. They could go on the Kinect or go on the Xbox system and solve that problem. That was a big breakthrough. Definitely, it had us beginning to look at all of our problems that we were admiring in a completely different way. And the one idea to keep in mind is that it's about, instead of programming all the rules, what we want is large data sets. So give me lots and lots of data, and the more the better, actually. The more examples you can give the system it can learn from, the better. And that's actually better than programmed algorithms, right? And that was the big breakthrough. So that led to things like Deepmind, if you've been tracking that from Google, how the Deepmind system was able to learn. That's me with Nolan Bushnell there. Nolan is the guy who founded Atari. He also founded Chuck E. Cheese, by the way, because he needed a place to put all of his games back in the day. But the Atari games, even though they're very simple, it might have been a simple matter to sit down and program the AI to play it really flawlessly. But instead, what they did is had Deepmind just watch people play the game. And by watching them play, it basically infers its own rules, and now it can play all the Atari games flawlessly, and of course at extreme speeds beyond human capability. So that was one breakthrough a couple of years ago. And the big one came last year, right, when it's one thing to have a computer system with some set of logic instructions in it defeat the number one chess player in the world. The chess game, although very complex in all of its moves and combinations, is something that has a good structure to it. So that was sort of understood. But having a system like AlphaGo actually beat the number one Go player in the world, people were predicting that it was still going to be decades before, or at least a decade before that actually happened. But it happened, again, faster than we predicted, where the number one Go player in the world was defeated by this system. And if you've ever played Go, the idea there is that, or the challenging thing about it was what you see there is that there's more combinations in that game than there are, I think they say, atoms in the universe, right? So it's a very complex system. And then this is the next big thing that shocked everybody. Last year, we were talking about, there are still some things that machines are not good at, like being able to understand the nuance of human expression and intention, or deception, right? So we were trying to figure out how long will it be before machines learn to lie? Can they beat the number one, the top Texas Hold'em poker players in the world? Or there's another game that's very popular in places like Korea, are these big matches on the game StarCraft, where again there's a lot of diplomacy and deception and teaming and that sort of thing. Well, earlier this year, if you were watching, a pretty basic set of machine learning libraries that had been taught the game of Texas Hold'em poker and how to read human intention and expression and deception actually defeated a group of the top Texas Hold'em poker players in the world. So things are happening again really, really fast. So let's talk about a couple of different ways to apply this. Now, the idea behind these machine learning brains is, and I'll tell you what we started doing with our little baby brain that we created a couple of years ago, is we actually took all human knowledge, right? So how do you categorize all human knowledge? And we started with just the Dewey Decimal System, right? Because taking the library as an example, and looked at all those different categories of information, and then just taught the system to read something, watch a video, look at a piece of content that it encounters on the internet, and then to classify it using that Dewey Decimal System. Initially, it was about 1,400 different areas of knowledge. And it was interesting to see and very compelling. And what's amazing about machine learning is seeing it actually increase its own understanding of the world. So today there's about 4,000 of those sorts of nodes in the brains that we're creating here. And that's very generalized knowledge. So it's everything from motorcycle maintenance to, to even understanding computer programming and artificial intelligence, everything that we focus on. So what's really interesting about it, though, and if you've watched IBM Watson develop over time, is when you can take that, instead of having this really broad, semantically extensive approach to knowledge, actually take it and focus it on something that's really bounded, like you hear IBM Watson going to medical school, or learning the tax code, or FASB rules, or revenue recognition rules. Something, the more you bound it, it still has this sort of broad capacity to learn, understand, update its database. And the more you can bound that problem, the more valuable and the more powerful the system gets. So one of the things we're doing here is we're actually doing that for small and medium-sized businesses, like architecture companies or accounting firms. And again, if we do this for an architecture firm, for example, we can teach the system or this architecture brain all about the practice of architecture. But then as the company begins to use it, it begins to develop into not just not just architecture, but the way that company practices it. You can think of it as a neural net, but where some of the nodes are made up of machine intelligence and some of the nodes are made up of human input. And that combination, again, that balance of humans and machines working together to perfect knowledge around something is extremely powerful. And I think every firm today needs to have that capability.